Yes, so let me go to our slide for which seminar of mathematical physics. Speak with Eugenia Boffo, is a researcher from Charles University, from the Mathematical Institute, and also from LMU Munich, based in LMU Munich, and she's going to tell us about classical basic cohomology. So yes, the stage is yours.
Yeah, thank you very much. Thanks for a very kind introduction, and I'm happy to have a possibility to tell you about this work in collaboration with Martin Sederman that appeared almost 2 months ago. So this is a computation of classical Milik cohomology that we did because there's been a paper about 6 to 7 years, no, sorry, it was 2015, so about 10 years ago almost, that found cohomology in negative degree produced by negative fields. That was therefore undermining the validity of some axioms that were suggested in order to show that the solution to the classical master equation is unique up to quasi-isomorphism. So that's something, a calculation that we done, and the solution to this puzzle was to consider the resolution of reducible constraints. The constraints were in fact reducible, and we did the resolution, and we found that the homology is eliminated by the resolution. So this is based on a very concrete physical model. We have an example in mind. It's not a general computation. So the model is, I will get this out of the way immediately. So it's the n=1 spinning particle, which consists of maps from an underlying supermanifolds. So we have maps from R, it's a line, super line, to some target space. In physics, we like to work with action functionals. So we take some integral over R1/1. Let's say we use some coordinates. I don't want to tell you which ones. And yeah, so an action functional is an integral of some function of a maps. In fact, there will be invariances. It's invariant under the diffeomorphism of the superlines, which, for lack of better naming, I will just label as generically algebra, but you have to think that it's super diffeomorphism of this line. So,
and you don't impose some how it's called field superfields, so you don't have a distribution there.
We are using so it's we have superfields. This is just a regular manifold, but this is a super manifold.
But do you have this distribution given by what it is theta de theta plus x de delta?
I think that's already like if you say it's R11,
Yeah.
already like you singled out the distribution.
Well, it's additional piece of structure, but okay.
Right?
We can.
Yes, sorry, you're right. No, sorry.
Okay.
Okay, so in fact, so the constraints are usually, so the fact that there is some invariance implies that therefore you can find the constraints. So if E alpha is an element of a dual of the algebra, you can write down this contracted functions, and for us, the alpha, we will have only 2 of them, and I will call them T and U. And later on, I will show you what they are, because I will give you a better coordinate description. But for now, n=1 spinning particle is a field theory of maps over a superline invariant under the super diffeomorphisms. Okay, and for the rest of the talk, so I'm gonna focus first of all on telling you how to do the resolution of reducible constraints. This guys here, and I wanna give some information about partition functions that we use just to understand the problem a little bit, but at the end of the day, it wasn't too helpful. And for the rest, well, I will eventually go on to say what really cohomology is and motivating axioms. And discuss why there was some cohomology classes that were found and how we eventually managed to remove these classes. So let's get started. So suppose you have a graded ring generated by some pi theta I runs from 1 to the dimension 3. And suppose you also have a metric theta by j. Minkowski metric should be fine. Now, you also have one tells you have these constraints.
So the grading is P is of degree 0 and theta of 1.
Theta I, theta j is of degree 1. I'm not asking for high. Now, if you want to know already, I don't know, the quotient of the symmetric algebra of P and theta by these constraints, well, it's better already, instead of just really calculating this to blow up do a resolution. So you start with a symmetric algebra here, the P and the theta, and then by writing like this with a symmetric algebra of the algebra satisfied by the constraints in degree by 1. This.
So you
And then here we project already to the quotient. That should be enough to resolve this quotient. And you will interpret this as a homological a quotient complex with some d0 that I will give you in coordinates. So suppose that here in G you have B and beta, and d0 then is defined to be. And obviously this will continue u d beta
B is even and it's shifted parity of T and beta is odd or vice versa.
This is odd.
Okay.
And this is the other way around. Yes, because the algebra itself is a superly algebra. Great. So this is for constraints. So now suppose that you are, and this is actually the case, there is a reducibility, and it means that you're able to find some relations among the constraints for some C alpha beta, some functions. So this is what it means to be, for a constraint to be reducible, and let me show you that this is the case for those two constraints. Of course, it means that they are set to zero. So suppose that omega is this gadget here, so it's 1 over d factorial of theta m1 to theta m d epsilon and d. So this is the relativity, so the tensor, so a bunch of plus or minus 1. And yeah, so this is the maximal polynomial in theta. Now also I want to have this operation, which is like now contraction of a theta I. So I remove a theta and I replace it with a p. So you will, yeah, I will write it here. With this, you can show that you applied it to omega, it's 0, just because you have already the maximum amount of thetas that you can symmetrize it or anti-symmetrize it due to the gradient. And yes, T omega minus U iota P on omega equal to 0. So there are the relations among these two constraints. Which means that you have to go on with projective resolution to take care of these extra constraints. They have to become boundaries for something, for some differential operator. So that is the other blackboard.
Can I ask?
Yes,
What's the signature of the metric theta?
I was thinking about, no, maybe let's do Euclidean, sorry. I think it's better.
So then in an orthonormal basis, capital omega is really just.
No, look, let's do Minkowski, sorry. It's better. It's better. So it's one plus one in diagonals. So then what's your question?
What is capital omega then? Is it really, this is a very silly question, but is it just the product of thetas or is it a
Right, it's a product of d thetas.
of all
One,
of them?
all of them.
It's like theta 1 until theta n.
Yes.
I was just yeah, I was just asking if there is a reason why to write it in this form. This is more like this.
Just I don't know, maybe there are more convenient ways. We just work with it.
I think it's fine.
Okay, so now I'm gonna extend the resolution over there with some extra contributions from some algebras described by reducibilities. This is shifted by 1, and then there is a D1. There's too much space. Projective proportion. So the important term here is D1. D1 can be given explicitly, and it is following. So it's now here I'm setting using this notation beta prime and b prime. Here still we have b and beta, and therefore one can do the computation and see that this is the differential that can extend the complex.
What was the head?
Just to denote it differently, because it's a different algebra now among the constraints because of the reducibility. Yeah, so, and you can go on because there can be also a reducibility of a reducibility when these relations can have relations with each other. So, yeah. But now, so the question is, are we really able to compute this quotient to find the cohomology factor, because we're interested in cohomology. Are we able to extrapolate some information on the other stages of a co-chain complex? Not really. Let's use the partition function to extrapolate some information. This is already in the second part. So, what is a partition function? It's some polynomial constructed in partitions. So, suppose you have some vector space which is graded, that you, in fact, it's for this co-chain complex, so you have some differential. Now, the partition function is for V, is some, say, you want to use, I will give you the definition with only one variable, but you can extend it to have more variables. So it will be sum over the dimension of the VI. And you can show that this polynomial, in fact, computes the dimension of the cohomology groups for this co-chain complex when the differential scales like each di scales like -1 t to the 0 di. So if this is true, then PV of P is but you replace the dimension of a cohomology group in here. Okay, so this is the partition function. So the point of a projective resolution is to have a complex which is mostly acyclic in the sense that there is cohomology only in one slot. So the partition function should be able to catch the dimension of a cohomology there. But we would also like, since it's a polynomial, we would like to factorize it in order to know the dimension only of the vector spaces. For example, this stage here or here, what's the dimension of this as a vector space?
Sorry, it's probably a stupid question, but what do you mean with the DIs scaling like -1 T0 DI? I didn't really get that one.
Okay, so because I need to explain it poorly. So let's say that okay, so maybe already let me introduce maybe already the example. So say that you have two graded degree 1 coordinates, θ1 to the 2 only. So I 2 in the example before, and I'm removing the pi now. I can write a partition function just by telling you each θi scales like θi, and the polynomial would be just because I can form let's call it singleton. I can form θ1, θ2, and I can form θ1, θ2. And since these are graded coordinates, right, θ1 squared and θ2 squared is 0.
What are the DIs then in this example?
I hope I got this right. So the DI are
Okay, it's just a
differentials in denoted them differently. I have urge to do that because I know that I think you can touch. So VI is H of VI, direct sum with the image of VI, direct sum with the image of VI plus 1. I think if we are saying that it's a differential, not a boundary, and therefore, well, then if you do this for the dimension of these vector spaces, you will find out that this combination cancel each other out if the differential is spaced like this. So you will end up only with this part. Sorry if it's a bit hand waving. Now, so let's go back to this example. In fact, I want to tell you that so sometimes you can really compute the repartition function, but if you are interested in knowing what's happening at the various stages of the resolution, it's complicated to factorize the polynomial, and I don't know much about it, about the factorization of polynomials. So, okay, so in this example again, now still theta 1, theta 2, but now with constraint. Theta 1, theta 2 is equal to 0. Now you can come using this conventions as before. I'm convinced that this is the whole partition function. However, if you're interested, for example, in knowing the contribution due to the constraint, maybe let's write it like this. Sorry, not so great notation. You will see, well, it's a 1 minus t squared. And this was a repartition function for the free case without a constraint, and already it's not true, and you need other factors, and this is a bit harder to find out which factors you need. But we want this kind of information. So to summarize with this example, I want to tell you that when you're working with graded rings and you want to know some information about these cohomology groups, either you are already quite lucky and you know the whole partition function, but maybe you don't know the factorization, or you might not even know. So what information do we have in our work? So maybe I can start passing this around. So there we've done some computations. So we had that. So let me go back to we were computing. It's also convenient to do the log of this because let me tell you, maybe not starting from the middle. So let's go back to the n equal 1 spinning particle case with p and theta. So let us say the p scales with t, but theta scales with s. You can use any scaling that you like. It's not a unique choice, of course, but this work, and you can show that some say that box is the fundamental is shorthand for the dimension of the fundamental, but it's also related. Okay, so of SOD. There is an underlying SOD symmetry because this can be interpreted as some SOD tensors, for example. So like this, and then so this pattern is the partition function for the graded ring without constraints, without reducibility. Now here you have the first constraint. You see it's the theta dot t constraint, so it contributes with s times t to the polynomial. Then there is 1 minus t squared from the t squared equals 0 constraint. And then when you go on with the others that we found, And then, so you can develop this polynomial, take the log of this, in fact, multiply all factors together, and it turns out that we were able to collect some simple young tableau with some quite simple book structure, but we were not able to see more structure in this and figure out the factorization of this polynomial, which is unfortunate, but for the purpose of showing that cohomology class found in the past will be eliminated, this was already enough.
Is it clear to see why it will be polynomial, not rational function?
I think it should be possible to show it. I cannot do it right now, but
And it will be also some best with. Okay.
of course, maybe something else, some other comment I can add here is that if you work in dimension 1, then you only have precisely 1 theta and 1 p generating your data. So then, well, you know exactly what the partition function should be. Would be 1 minus x plus p. Yeah, it's complicated to factorize within a final result. Okay, so now it's time to erase this left button. And I'm already at the third part. Now I want to tell you what these celebrated axioms that define the ability variety are. And it's 3 of them. They're all very reasonable. That's why when there is a calculation that violates these axioms for a simple model, then you will be wondering, are we doing physics correctly? Or these axioms are really correct? But they're all so reasonable that I don't think it's have to give up on them. That's why. What we've done. So, these are axioms for finding ability variety. Which is work of Felder and Kashdan from 2012. So now we are also in the context of a BD, the field theoretical BD situation. So we need consider a natural example of a symplectic manifold, which is the shifted cotangent bundle to some shifted to some manifold, and I'm gonna keep this shifted algebra explicit. I will talk about the generators here as the ghost, and as section of a cotangent, the fibers as anti-fields or anti-Gaussian fields. That's the standard nomenclature.
Sorry, is G ordinary superalgebra, or is it like a delicate one?
Good point. So I think it's ordinary. Have to look up.
Okay.
Now let S not be function only on this manifold here, and S a function this manifold instead. Super manifold. I will write it very pedantically. But then let me call it maybe A equal to then and let I be the ideal generated by the fields in positive Gaussian degree. The Gaussian degree is this cohomological degree.
So this M is a manifold for dimensional spacetime. It is not purely M. It's for long.
I kept curly M to refer to maps.
Maps.
So the spinning.
So you take that M space to maps.
Yes.
Okay.
So then the axioms are S restricted to M is equal to S0. Which is a so-called classical master equation, and for some bracket it's for one corresponding to this reciprocative structure on this cotangent manifold, and three, which is the important one. So A mod I has no cohomology in negative Gaussian degree. So the non-positive fields will contribute no homology in negative Gaussian, in negative degree. So then this is a definition of a biparallel. And yeah, these axioms were used to show that once you have a solution to the classical master equation that is unique, I think up to quasi-isolated. In the paper, we talk about the stable equivalences, but I'm not too familiar with it. We just looked at these axioms because, in fact, there's been work shown that there was actually cohomology violating the form of this third axiom. So that's what filter out Gessler. It was cohomology for the equal one steering particles. Gessler 2015 found some violation. Some homology clusters in the original diagonalities, and I will then tell you later how we look like, but we'll go the explicit expression. let's write that this is cohomology class in I with negative cross degree. Maybe let's say something like this. You see what this symbol is. Now, okay, in this carton, I would just like to rewrite the spinning part of the model again in a field theoretical setup, because for now, when we were discussing the resolution of reducible constraints, we used the algebras, rings, we use the coordinates. So now I need to translate this into a more field theoretical statement. So I will use okay, but maybe first let me just we will have x a c. So x will label collectively the xi, but pi and the theta. Before I didn't mention any xi because they don't really make any difference, but they could be luring in the background. And then in and psi are therefore these generators of the coalgebra, the algebra of the diffeomorphism of a superline. So this is a Einbein, and this is the superpartner of the Einbein. And the C are already in the shifted algebra, so it's collective nomenclature for the Gauss C and the Gauss gamma are related to this. Now, in the shifted cotangent bundle, there will be also X stars, A star. That would be the notation for the fiber coordinates.
So, just to understand this point, so you're saying that in the example that you showed, so for the M1 spinning particle, this does not always satisfy the definition on the left-hand side, because the
Yes.
third axiom might fail. Yeah. So this,
Violated the axiom number 3.
so it's just saying that this is not a special case of the definition on the left-hand side. It's something more general. Different.
Yes, but that was I think we realized that the computation was missing the whole resolution, well, at least the other steps of the resolution of the reducible constraints, because the constraints will still be and u. And I've already told you that these are reducible, so you can find out other, can extend your differential with other contribution, and you can show that some this cohomology class becomes a co-boundary.
So you're saying what is written in this paper is wrong, or was okay? Interesting.
Well, it misses a detail.
Mhm.
Right. So let me just briefly write down. So it's a field theory. I will use integral. I will avoid writing the volume form, but let's say just let's write it like this. So this is the S0 from before, from there, with d of xj equal to, there is a, let's say, doctor, maybe let's d over d tau, for the tau is the bosonic coordinate on the superline, and then there is also extra yes, so this part is it's gonna implement is related to the constraints. A alpha are exactly the coalgebra elements. Now, if you are familiar with this, you will realize that there are already some contributions which are respectively linear in the ghost fields and quadratic in the ghost field. And if the system didn't have reducible constraints, S0 plus S1 plus S2 will be already the good action function that satisfies the classical consideration. So I will just write them down for completeness. Maybe okay, there are some sign because everything is graded.
So is this integral is over?
Line. Yes, not even the super line anymore because that integration is already done. And then there is C alpha C beta, C alpha beta. Yes, so there are some, again, some structural constants, even here. Symmetry. Yeah. But already, for example, now, so we're interested in canceling homologies, discarding terms that belong to the ideal, right? So one prime example of a homology which is removed is already in this very general setup that you can then specialize to a spinning particle. It's as follows. So one, I will call it like this, one cohomology class is, sorry, because I used, okay, with the notation from before, now sorry about this, but so these are the functions used in the general statement that there is a reducibility when this is mutual. Okay. Sorry about notation. Then, right. So this is one, in fact, sorry, this would be a homology class, but you can show that it's cancelled in by applying X. S not plus S1. That's it, enough already to cancel it. Because it will give you exactly T alpha plus something else that lives in the ideal. So, but this is 0 because
It's called the
it's
Poisson package or?
yes. Then no, sorry. Sorry, this will help us to cancel a constraint to make them trivial in homology, because we know that so that's 0. In order to make this trivial now, we need to construct an extra action functional that I will label A prime star. So you need an extra generation of, let's call them Lagrange multiplier, an extra generation of those A, whatever they are. I'm not going to be explicit, but so the point is that this would be in Gauss degree think it's +1, and this is the gross degree -2, because it's the symplectic dual, and we have a shift. So this is the expression that you can find, and now able to. So this is also A prime, and there is C alpha, alpha prime, beta prime, it's A prime, B prime, C prime. So this is also in total gross degree 0, because this is one, this +1. Sorry. No, sorry. That's why I'm confusing myself over my own notation. It's not degree. This is -1, +1, +1, and -2.
Sorry, now we are changing a bit this purely I, right? This manifolds on which we are working.
Yes.
So now it's not just the
Yeah, but it's not
one,
fixed.
we added
No,
more
that's-
features.
Yes. Yes. So, great. So this is another term, and but since we had to introduce some new coordinates, this can produce extra homology that you have to cancel step by step. Perhaps makes sense to tell you that we know what the cohomology at the new degree will looks like. So maybe some lambda2. Just to convince you that we don't stop right just after canceling this dangerous cohomology class, but we can go on. The only problem is that we don't know the whole resolution, so we cannot go on until the end. So maybe that's just a partial result, but at least so. So this is just to convince you that you can go ahead for a few more steps. But now let me comment on this. Zeta K of F. So this is the cohomology produced by non-positive Gauss degree fields in negative Gauss degree. So it's written like this. Sorry, it's a very common and dependent exercise. So psi star are dual to the A star, and then there is the K -1 E star f of x omega minus psi star K f of x dot p omega. But we find instead, and we have been able to show that psi 1 is what we find in our paper. And it's like this, so it's exactly, well, as you can guess, I've already written this down in a different notation, because before switching to VB, I was talking about some resolution of a ring. So now, for conversion, let me just say that the B and beta are turned into, so these are the, I think, the A star. If I'm not wrong. Yes. So what I've written before, so now it's been erased, but maybe you have a good visual memory, so it's exactly E star omega minus psi star. But converted, it was some D1 of a resolution and was given by the omega minus beta delta p omega plus. Oh, sorry, there is probably a minus. And then there was a with respect to beta. So this is what was in the article. This is what we find, and by all the steps of a resolution, we can say that this cohomology class is in fact a coboundary of some differential operator, which is the Poisson bracket of S0 plus S1 plus S2 plus SA prime. A prime star. And you can see, I mean, maybe something to convince you, for instance, is that this is in fact lives here, right? Because I'm not using anything positive. Everything starred is usually at least in Gauss degree -1. And whatever is in Gauss degree 0 can be there. And yes, and it's of total degree negative. So this is -1. This would be minus k plus 1, suppose. K. Yeah. So, I mean, that's the conclusion. Sorry for a lot of very explicit formulas which are not so easy to handle. Thanks for attending.
So time for questions. One of the questions also from the online audience. First.
So, to understand correctly, this filter variety.
Yeah.
This refers just to ordinary BRSP reducing, right? That's true. You have just the Lie algebra, like the symmetries, and you add, and you add just those for these.
No,
This
that
is
maybe
one.
maybe this is. I should have literally copied from their article. So maybe take something generic that you know it's a tangent bundle of something.
Right, but that's the question, my question about this something.
Yeah. Yes.
Because this something, it depends very much on whether you have constraints, whether you have
Yes.
constraints for
Yes.
constraints, whether your algebra closes only on shell, and
Yes.
so in general, it's much more complicated.
Yes. But I don't think that they were being explicit about. So this is what I wrote, but I think they were very. They were not specifying. That's why.
Because
Has been-
Andre mentioned you extended.
Yes. Yes.
Also, right?
Yes,
Because
yes.
you have now constraints between constraints. Therefore, you add those for those.
Yes.
And therefore you also change the differential. So the
That's
concept is different, right?
Sure.
Okay.
Sure, but so I should go back to the paper, but I think they were just very general. They were not fixing the
Can you say
variety,
it's like didn't consider this
reducibility and multiple
accessibility and
constraints.
therefore
Yes,
it didn't add growth for growth.
yes.
After you added this new, that you did this extension and you get this new active, is it now an AKS theory? Or the original theory AKS?
The original theory was already AKSL, and now it's still an AKSL after, yes.
So with a different target?
Yeah.
What happens to the, because before the target was just normal M, right?
Right. We have a chapter on that, so I don't know if you remarks it, maybe we can have a look.
And you also have this different work where you handle quantization of the target and you compute the cohomology and show that it's 0 in negative degrees. Do these two calculations relate in any way?
Which calculation are you referring to? Do you have a, are you saying I've done it already? No, because it's different, so over there we are, this is all classical, right? And instead in that computation, we are also quantizing the target, so we are going to a Lagrangian submanifold, and then it's different, and you don't find the cohomology due to negative ghosting or non-positive fields in negative degree by construction, in fact.
Okay. It's because of just degrees of the Lagrangian, or
Yes, yes.
so it's not because of the canon of the quantization.
For me, canon of the quantization is choosing a polarization, right? So
Okay.
the degrees of the Lagrangian.
Any more questions? Okay, I guess we can thank the speaker then. I will see you next. I don't remember. Right? Some. Maybe. Oh,